Okay, now as you might have guessed, the real fun is going to come when we start to introduce a strong acid or a strong base. Or not a strong acid or a strong base, sorry. My cat has figured out how to bother me while I'm trying to do this to get treats. What happens when there's a weak base or a weak acid in here? And then equilibrium becomes an issue here as well. So in this case, we have hydrochloric acid, HCl, which is a strong acid, reacting with ammonia, which is a weak base. So we really need to consider two reactions happening here. The first is the reaction of HCl with the weak base. Because there's a strong acid involved, that is a one-way reaction. So HCl is going to react with NH3, and that's going to produce NH4 plus ammonium. That's going to be the conjugate base of NH3, and chloride ion is going to be the conjugate of HCl. Now it's not a base, so I wouldn't say conjugate base, it's just the conjugate. Now notice there, that's where your Bronsted-Lowry definition is a little bit different than your Arrhenius. Acid base, and we're not producing water, we're just moving the proton back and forth. Now since this is a one-way reaction, I use the one-way arrow there, I like to think of this as an if chart, not an ice chart. We've got 20 mils of 1 molar HCl, 20 mils of 1 molar ammonia. Now we saw that calculation before, so let's write it down again just for clarity's sake. 1 molar means 1 mole per liter, and I'm changing liters directly to milliliters here to kind of save a step in my problem. But that would be 0.02 moles of HCl, and since it's the same amount of ammonia, it would be 0.02 moles of ammonia as well. And that means we don't really have a limiting reactant here. They're both the limiting reactant, which we would refer to as stoichiometric. We've got just the right amount of each of those. That means they're going to react completely with each other. Final conditions, we wouldn't have any of the HCl or the ammonia left, but we will have 0.02 moles of ammonium. Now, here's where we have to analyze a little bit. We should recognize chloride, again, it's the conjugate of the strong acid. That's not going to be a base. It's not going to have any effect on the reaction. But ammonium is the conjugate acid of the weak base, and that means it is in itself a weak acid. So this 0.2 mole left over is going to influence the pH of our solution. So again, with the if chart, it's moles, but with an ice chart, it's going to be concentration. So let's change that to the concentration of ammonium in our solution. So 0.02 moles. We now have a total volume of 40 milliliters when we add these together, so it would be 0.04 liters. So this solution would be 0.5 molar. Right now it's really like a 3 significant figure, 0.5, but to keep from getting zeros all over the place, I'm leaving off those trailing zeros for most of the problem. So 0.5 molar is my concentration of ammonium. That leads us into the second reaction we need to consider, which is the fact that ammonium is a base. It's not a base, it's an acid. It's reacting with water, and that's going to protonate the water, so we'll get some hydronium, and that will allow the conjugate base of ammonium, which is the base form ammonia, to form. And we can do a little ice chart for this guy. Right now, ammonium, we start as 0.5 molar. Before the equilibrium, we don't have any of the products. That means we're going to lose some of the ammonium. We're going to gain some hydronium and some ammonia. And we'll have 0.5 minus x, and x by the time we get to equilibrium. Now, here's another thing you may have to watch out for in this type of problem. We've got a weak acid here, and we don't have a Ka, right? So you've got a textbook, you've got the internet. Sometimes you've got to look up, what is the Ka I'm interested in? What is the Kb I'm interested in? In this case, Ka for ammonium is 5.6 times 10 to the minus 10th. Okay. Now, just looking at that, initial concentration 0.5, equilibrium constant this small, right? This assumption is going to be pretty good. in terms of removing the minus x. But let's calculate it out just to be safe. If I take my concentration I'm starting with, divide by the Ka value, that is 0.5 divided by 5.6 times 10 to the minus 10th, and that is 8.9 times 10 to the 8th. And yeah, that's a little bit more than 1,000. So this is a pretty good assumption here for this particular problem. So if I take that value, I plug in what I know is going to be the equilibrium constant expression here for my weak acid. That's hydronium, and the conjugate base, ammonia in this case, divided by just the weak acid on the reactant side since we leave out the water. Right? Both of those in the top are x. Ammonium started as 0.5. Right now I have an equation I just need to solve for x. So if I take 5.6 times 10 to the minus 10th, and multiply through by 0.5, right? And then if I take the square root to get rid of the x squared term, so square root of my previous answer, I get x is equal to 1.67 times 10 to the minus 5th, and that's going to be a molarity. Now, x in this case is hydronium ion, so to get to the pH, I can take the negative log of that. And that will give me a pH of 4.78. Okay, so yeah, that's not neutral, right? So we do have to recognize that even though we had a strong acid and weak base that were equivalent amounts, right, what's left over still does have an influence on the pH.